Every year, the world's tomato processors turn somewhere around 50 million tons of ripe tomatoes into juice, paste, ketchup, and canned soup. And every one of those tons leaves behind a wet, red, foul-smelling residue of skins and crushed seeds that nobody at the factory actually wants. It is too heavy with water to ship any real distance, too rich in sugar and nutrients to sit in a pile for more than a few days without rotting. And for most of the industry's history, the only real answer was a truck to the nearest landfill. Then, a small research group on the southern coast of Spain looked at that same slimy waste and asked a very different question. What if the toughest part of a tomato, the waxy skin built to survive sun, rain, and insects on the vine, could be turned into a plastic bag that survives a grocery trip and then quietly dissolves in seawater within about a month? This is the story of how the ugliest leftover of the ketchup industry became a source of medical-grade antioxidants, cattle feed, cosmetic oil, and a biodegradable plastic that might outlive its own inventor's expectations. And it starts with a number most people have never once thought about. How much of a tomato never actually becomes food? Start with the tomato itself. Global growers produce close to 189 million tons of it a year, more than almost any other vegetable crop on Earth. Roughly a quarter of that harvest, somewhere between 46 and 50 million tons, never reaches a produce aisle at all. It goes straight into industrial processing lines to be crushed, cooked, and reduced into paste, juice, and sauce. Three places dominate that pipeline. California alone grows about 95% of all the tomatoes processed in the United States, and on its own, accounts for roughly a quarter of global processing volume. China has built the fastest-growing tomato processing industry on the planet, almost entirely concentrated in one region, Xinjiang, in the country's arid northwest. The industry there started in 1978, with help from Italian traders who brought over the processing know-how, and the first tomato paste production line went up in Xinjiang in 1984. Growth stayed modest for a decade, around 30 processing companies by the 1990s, all producing strictly for export, before accelerating hard. By 2009, Xinjiang alone was turning out just over 1 million tons of tomato paste from 100 separate producers. Today, the region processes up to 3.8 million tons of tomatoes a year, accounts for more than 80% of China's entire national tomato output, and ships finished paste to more than 130 countries. What started as a handful of Italian-trained factories in a desert province became, within 3 decades, the backbone of the world's largest tomato paste export industry. Italy rounds out the top 3, smaller in raw volume than California or China, at around 5 million metric tons of processed tomatoes a year, but still responsible for roughly 13% of global processing and nearly half of Europe's, built less on sheer scale and more on prestige. The country's most famous export, the San Marzano DOP tomato, grows exclusively in a protected zone of Campania's Sarnese-Nocerino Valley, feeding a premium, name-brand supply chain that shows up on pizza restaurant menus and supermarket shelves worldwide. Together, these 3 countries process well over half of everything the planet turns into ketchup, sauce, and soup. That scale did not happen by accident. It was built, deliberately, starting with one company. When Henry Heinz began selling his tomato ketchup in 1876, it was a small regional product competing with dozens of others. By 1905, Heinz had become the largest ketchup, pickle, and vinegar producer in the United States, turning out roughly 5 million bottles a year. 2 years later, that number had more than doubled to 12 million bottles, shipped as far as Japan, South Africa, and Australia. By 1919, the company was running 25 factories and employing more than 6,000 people, and it had pioneered the sanitary, mechanized processing lines that the rest of the industry would eventually copy. Every other tomato processor that followed, in California, in China, in Italy, inherited that same industrial logic. Crush tomatoes at enormous volume, as fast and as cleanly as possible. Nobody in that race was thinking about what to do with the skins and seeds left behind. They were thinking about bottles per hour. Every ton of tomatoes that goes through that crushing and straining process leaves behind pomace, the skins, the crushed seeds, and a small amount of leftover pulp. Estimates for how much pomace a ton of tomatoes yields vary by source, running anywhere from about 4 to 10% of the processed weight. Researchers studying the industry put a real number on that mountain, somewhere between 6.2 and 9 million tons of tomato pomace generated worldwide every single year. Exactly how much of that pomace is seed versus skin depends on who is measuring it. Feed industry references put the seed content at a modest 5 to 10%, while researchers working on the bioplastic side describe pomace as split almost evenly, with peels making up roughly half and seeds closer to 40%. The two numbers disagree, and the honest explanation is probably that they're measuring different things. Different tomato varieties, different processing methods, different points in the pipeline. What both sides agree on is simpler. This is not a small, easily ignored stream. It is millions of tons of biological material generated every year, and it does not sit quietly. Left wet in a pile behind a factory, it starts to smell within hours and mold within days. Which raises the obvious question: why, after more than a century of industrial tomato processing, is most of that mountain still being dumped instead of used? The honest answer is that tomato pomace fights you on nearly every front at once. The first problem is water. Depending on how a factory processes its tomatoes, fresh pomace can be anywhere from 45 to 80% water by weight, commonly cited at around 3/4 water. That means a truck hauling pomace to a distant processing facility is mostly hauling water and paying diesel fuel prices to do it. For any product where the pomace has to travel more than a short distance, the economics collapse before the material even reaches a factory gate. The second problem is speed. Pomace is wet, sugar-rich, and biologically active the moment it leaves the crusher, which makes it an ideal home for mold. Fungal contamination from species like Penicillium and Aspergillus is a well-documented risk across tomato products in general, and some of those fungi are the same ones responsible for aflatoxin, a genuinely dangerous toxin that can build up in improperly stored feedstuffs and sicken the livestock that eat them. That single fact turns pomace from a free byproduct into a material that has to be dried, ensiled, or used within a very narrow window, or it becomes a liability instead of a resource. The third problem is subtler, and it comes from the very thing that makes a tomato useful in the first place: its skin. Pesticides sprayed on a tomato plant tend to concentrate most heavily on the skin's outer surface, which means pomace, being mostly skin, can carry a higher residue load than the whole tomatoes it came from. For a processor thinking about turning that pomace into cattle feed, human food ingredients, or cosmetics, that is not a minor footnote. It is a quality control problem that has to be solved before anything else gets built on top of it. There was, technically, always a fourth option: composting. Left to break down slowly in open piles, pomace does eventually turn into usable soil amendment, and plenty of processors have done exactly that for decades. But composting is slow, land-intensive, and produces a low-value bulk product. It solves the disposal problem without ever coming close to capturing the lycopene, the cutin, or the oil sitting inside the material the whole time. It was less a solution than a way of making the problem smell less bad while it disappeared. Stack those three problems together: too heavy to move, too fast to spoil, too easy to concentrate contaminants, and you get the real reason most of the world's tomato pomace has spent the last century going to only two places, plus a slow compost pile for whatever didn't fit either one. In California, where dairies happen to sit right next to the processing plants, pomace gets fed to cattle, fresh, before it has time to rot. Everywhere else, especially across the American Midwest, most of it has historically gone straight into a landfill. And landfilling food waste in general now runs upward of $60 a ton in tipping fees alone, before counting the trucking to get it there. That is not a rounding error for a processing plant handling pomace by the thousands of tons every season. But landfilling a nutrient-rich, lycopene-packed, cutin-covered biological material was never really a solution. It was just the industry admitting it hadn't found one yet. And landfilling organic waste is not a neutral choice either. Food waste breaking down in landfills is a meaningful driver of global methane emissions, a gas roughly 80 times more potent than carbon dioxide at trapping heat over a 20-year span. And food waste as a category is estimated to account for around 8% of total global greenhouse emissions. Every ton of tomato pomace sent to a landfill instead of a digester or a dryer wasn't just a wasted resource. It was an active liability, quietly working against the same climate goals the rest of the food industry claims to care about. Something had to change the math. The first real crack in that stalemate opened in 1995 in Beersheba, Israel, when a small company called LycoRed set out to do something nobody had tried at commercial scale. Extract lycopene, the deep red antioxidant compound that gives tomatoes their color, and turn it into a standalone ingredient. LycoRed partnered with scientists at Hebrew University and drew on genetic material from Israel's Volcani Center to help develop a tomato variety bred specifically for higher lycopene content. The company built its flagship product line, LycoMato, around that single compound, proof that tomato biomass, including the parts a factory would otherwise throw away, could be treated as a chemical feedstock rather than garbage. The underlying science had only recently caught up to the opportunity. In 1989, researcher Paolo Damascio and colleagues had shown that of all the carotenoid pigments tested, lycopene had the single strongest capacity to neutralize singlet oxygen, one of the more damaging reactive molecules that builds up in human cells. That finding gave LycoRed's entire business a scientific foundation to build on, 6 years before the company existed. It was a narrow win, focused on one valuable molecule inside the tomato, but it planted the idea that pomace wasn't worthless. It was simply unrefined. The second turning point took nearly 3 decades to arrive, and it came from a completely different angle, the skin around the tomato, rather than the juice inside it. At Spain's La Mayora Institute, a research group led by José Alejandro Heredia had spent years studying cutin, the waxy protective biopolymer that coats every tomato's skin and helps it survive sun, rain, and insect attack while still on the vine. Chemically, cutin is a natural polyester built from long, hydroxylated fatty acid chains, and it is both non-toxic and biodegradable by design. It is, after all, meant to break down eventually in nature. Heredia's group found a way to extract that cutin from tomato processing skins and rework it into a genuine plastic-like material. The real test came when they took a strip of their finished material and submerged it directly in seawater, then simply waited to see what would happen. The same fate any piece of ocean plastic eventually meets, except this time by design instead of by accident. Within about a month, the material was gone, broken back down by the same marine microbes that spend centuries failing to make a dent in ordinary plastic. That result is the detail that turns this from a lab curiosity into something worth building an episode around. A plastic engineered to fail, on a timeline measured in weeks, compared to the roughly 450 years a conventional petroleum-based plastic bag is estimated to take to break down in the same environment. Around the same time, a separate academic effort, the POMOPLA2 project, led by researchers including Rotondo and colleagues in 2025, approached the same waste stream from another direction, developing a bio-based composite that blends tomato peel byproduct into a plasticized PLA matrix, aimed squarely at replacing the petroleum-based PET, PE, and PP plastics used in ordinary food packaging. 2 research groups, working the same rotting factory waste from 2 different technical angles, had landed on the same conclusion. The part of the tomato built to survive the outdoors was exactly the part that could replace plastic that refuses to leave the ocean. None of this arrived without doubt, and the doubts were reasonable ones. The first is about safety, not ambition. Turning wet, mold-prone pomace into livestock feed sounds simple in theory, but it is not a free lunch. Skip the drying step, skip the ensiling, cut a corner on storage temperature, and you are not saving money. You are gambling with aflatoxin contamination in a product that ends up in milk and meat. Every serious feed use pathway for tomato pomace has had to build quality control in from the start, not bolted on afterward. In practice, that means testing incoming batches for mold before they ever reach a mixing trough, and drying or ensiling pomace fast enough that the fungi never get the days of warm, wet conditions they need to establish themselves. Processors who skip that step are not saving time. They are exporting a problem downstream, onto a dairy herd that has no way to inspect what it's being fed. The second doubt is more fundamental, and it is the one that has kept most of the world's tomato pumice out of any high-value pathway at all. Does turning pumice into lycopene, oil, or bioplastic actually make economic sense once you account for the same water weight and short shelf life that made it a disposal headache in the first place? There's a quieter version of that same doubt specific to the pesticide residue problem. If pumice concentrates whatever chemicals were sprayed on the original crop, is it really safe to turn that same material into a face cream or a food-adjacent fiber additive? The honest answer depends entirely on the pathway. Extraction processes that pull out a single purified compound, lycopene via supercritical CO2, cutin broken down into its fatty acid building blocks, leave contaminants behind in the spent material, the same way distilling alcohol leaves impurities in the still. Pathways that use the whole, undivided pumice, like feed, fiber flour, or compost, carry that residue risk forward and have to be tested for it directly, batch by batch. It's not a reason to abandon any of these uses. It is a reason none of them get to skip quality control and call themselves finished. A tomato skin bioplastic that biodegrades in the ocean is a remarkable material. It is also, right now, a research stage material, the product of academic groups like La Mayora and POMOPLA2, not yet a line item on a factory's balance sheet. Skeptics inside the processing industry have a fair question. Can any of this scale past a laboratory bench, or will pumice keep going to the two places it has always gone, the nearest dairy or the nearest landfill? The European Union's own waste framework offers a partial, institutional answer to that skepticism, rather than a marketing promise. Since Directive 2008/98/EC introduced end-of-waste criteria, certain byproducts, including agricultural bio-waste like tomato pumice, can legally exit waste status entirely once they're processed to a defined standard, clearing a real regulatory path for companies to sell what used to be a disposal cost as a product instead. That does not settle the economics on its own, but it means the doubt is no longer just, can this work chemically? It's, can this work at a price point? Which is a very different and more answerable question. The answer so far is that it depends entirely on which piece of the pumice you're chasing, because skins, seeds, and pulp each go through a completely different transformation. Lycopene extraction starts with drying the pumice to strip out that stubborn water weight, then pulling the red pigment out using supercritical carbon dioxide, CO2, held under enough pressure and heat that it stops behaving like a gas and starts behaving like a solvent, dissolving lycopene out of the dried material without leaving behind the toxic solvent residues that older extraction chemistry used to produce. Run at around 300 bar of pressure and 80 degrees Celsius, the process can recover roughly 80% of the lycopene and 88% of the beta-carotene locked inside dried tomato skins. What comes out the other end is a concentrated, food and cosmetic-grade antioxidant, the same compound LycoRed built an entire company around back in 1995. Run the seed fraction of the pumice through a cold press instead, sometimes after an enzyme, microwave, or ultrasound pretreatment to squeeze out a better yield. And the result is tomato seed oil, a pale, non-greasy oil that is roughly 80% unsaturated fatty acids and still carries some of that same lycopene antioxidant punch. It shows up today in moisturizers, anti-aging creams, lip balms, and hair products, marketed by boutique cosmetic brands explicitly as an upcycled ingredient recovered from food industry waste rather than grown for its own sake. The skin fraction takes the most technically demanding path. Its cutin coating has to be separated out and chemically reworked into a usable plastic feedstock. The process Heredia's group at La Mayora refined into a material that behaves like ordinary plastic on the shelf, then breaks down in the ocean instead of drifting there for centuries. In one version of the process, researchers blend the fatty acid fraction extracted from tomato pumice with beeswax and sodium alginate, then bake the mixture at 150 degrees Celsius for 8 hours, essentially polymerizing the fats back into a waxy, water-resistant film that behaves almost exactly like the natural cuticle on a living tomato's skin, hydrophobic, tough, and flexible. A related biomimetic film, built by layering a similar plant cuticle-inspired coating onto conventional PLA plastic, achieved complete biodegradation in soil in just 5 weeks, while still improving the material's mechanical strength rather than weakening it. The POMO-PLA2 approach blends that same peel byproduct into a plasticized PLA matrix, aiming at a more immediate target, replacing the everyday PET, PE, and PP plastic used in food packaging, without needing an entirely new manufacturing pipeline to do it. There is a fifth pathway hiding inside the same cell walls that produce cutin: pectin, the gelling agent used across the food industry in jams, sauces, and processed foods. Green extraction methods, ultrasound, microwave, and high-pressure techniques have pushed pectin yields from pomace as high as 35.7%, more than 8 times what older solvent-based extraction could recover. And some of the same processes can pull out pectin and carotenoids together in a single pass, making the extraction more efficient on both fronts at once. A sixth pathway runs in the opposite direction entirely. Instead of extracting a single refined compound, some processors dry the whole pomace down and grind it into flour. Because tomato pomace is naturally gluten-free and unusually rich in fiber, commonly 60 to 70 grams of it per 100 grams of dry material, alongside 10 to 20 grams of protein. It has been tested as a fortifying ingredient in gluten-free pasta and extruded snack foods, aimed at a gluten-free food market valued at roughly $14.1 billion in 2025, and projected to reach $33 billion by 2034. It is an unglamorous use that solves a real problem. Most gluten-free snacks are made from refined starches with almost no fiber or protein in them, and tomato pomace fixes both gaps in a single ingredient. Even the least appealing option, just breaking pomace down for energy, turned out to have its own complications. Anaerobic digestion, the same bacterial process used to turn manure and food waste into methane-rich biogas, works on tomato pomace too, and tomato waste in general has a methane potential roughly comparable to corn stover, a widely used bioenergy crop. But tomato plants also produce natural antimicrobial compounds, glycoalkaloids called tomatine and tomatidine, part of the plant's own defense against fungi, and researchers running early digestion trials found that residual tomatine in the pomace measurably suppressed the very bacteria that were supposed to be breaking it down, cutting into biogas yield. It was a reminder that even the just throw it in a digester option came with its own wall to climb, not a shortcut around one. And the fraction nobody has to reinvent anything for is the oldest use of all: feed. Dried or ensiled into silage, pomace has been tested directly against standard maize silage in dairy cow and lactating buffalo rations, and in both cases, researchers found no meaningful difference in dry matter intake, milk yield, or milk composition. It is the least glamorous use on this list, and also the only one already operating at real, everyday scale, quietly running through California's dairy country every single processing season. Add it up, and tomato pomace is no longer a single waste stream. It is the raw material behind at least 4 separate real markets at very different stages of maturity. The most established is lycopene itself, valued at roughly $142.6 million in 2024, and projected to climb toward $247.7 million by 2033, driven by demand for natural antioxidants in food coloring, supplements, and skincare. LycoRed, still operating out of Israel 3 decades after it started, remains the clearest example of a company built entirely around treating tomato biomass as a chemical resource rather than a waste product. Tomato seed oil sits one tier below that, a smaller, faster-growing niche inside the broader natural cosmetics boom. In March 2025, the Australian ingredient company Native Extracts partnered with food giant Kagome to launch Red Velvet Oil, a skincare ingredient pressed directly from upcycled tomato seeds left over from Kagome's own tomato processing. Native Extracts founder, Lisa Carroll, called it proof of the power of upcycling waste into high-value ingredients, for a beauty industry increasingly built around exactly that pitch, turning another company's processing waste into your own premium product line. Bioplastic is the newest and most uncertain bet of the group. Both La Mayora's cutin-based material and the POMOPLA2 composite remain research and pilot stage projects rather than commercial products lining store shelves. Genuinely promising, genuinely unproven at industrial scale. Whether either one becomes the tomato industry's answer to ocean plastic, or simply an important proof of concept that someone else eventually commercializes, is still an open question. Pectin and gluten-free fiber ingredients occupy a middle tier of their own, riding on established, already massive markets. Pectin is a staple food industry ingredient. Gluten-free food alone is worth well over $14 billion a year. Rather than needing to create consumer demand from scratch the way a brand new bioplastic does. That makes them, in some ways, an easier commercial bet than the Cutin plastic, even if neither one gets the same attention. One more small but steady market sits alongside these. Pet food manufacturers have long used dried tomato pomace as a fiber source in kibble formulations, the same nutritional logic that works for cattle applied to dogs and cats instead. Proof that even the most basic use of pomace has already found more than one customer. And underneath all three of those newer bets, the oldest and most boring use of pomace, dairy feed, keeps running exactly as it always has, absorbing a meaningful share of California's pomace output because the economics of dairy right next door have never needed reinventing in the first place. What began as a wet, foul-smelling problem behind a ketchup factory has, piece by piece, been sorted into value. The skins that once just rotted in a pile are now, in a research lab on the coast of Spain, the raw material for a plastic that disappears into seawater within a month instead of persisting for centuries. The seeds that used to be crushed and discarded now show up, cold-pressed, in the ingredient list of a face cream. The lycopene that gives every tomato its color has become a standalone antioxidant business worth well over $100 million a year, and still growing. And the plain, unglamorous bulk of it all still does exactly what it has quietly done for decades, feeding dairy cattle across California, at a scale large enough that researchers have measured it against maize silage and found the cows genuinely cannot tell the difference. Line up every fraction of the pomace side by side, and almost nothing is left over anymore. The skins become plastic film or a waterproof coating. The seeds become cold-pressed oil for a face cream, or a pressed cake still valuable enough for feed. The fibrous pulp becomes pectin, or gets dried into a gluten-free flour additive. The whole mixture, undivided, still becomes cattle silage exactly as it always has. Even the leftover sludge after extraction, the fraction with nothing left to extract, can go into an anaerobic digester and come out the other side as methane gas, feeding a generator instead of a landfill. It is not a perfect system yet, and every pathway on that list is running at a different scale, from global industry, feed, lycopene, down to handful of research papers, bioplastic. But the era of one single answer, dump it, is over. None of these four pathways has fully solved tomato pomace's original three problems. The water weight, the spoilage clock, the pesticide residue risk still have to be managed at every single step, on every single batch. But for the first time, all three of those obstacles are being treated as engineering problems to solve, not reasons to give up and call the nearest landfill. Run the numbers on just the most established piece of this story, lycopene, and the shift becomes concrete. A market worth $142.6 million in 2024 is expected to add another $100 million in value within a decade, built almost entirely on a compound that used to wash down a drain with the rest of the factory rinse water. Multiply that by every other fraction of the pomace now finding its own buyer, and the outline of a genuinely different industry starts to take shape. One where a tomato is no longer just a fruit that becomes ketchup, but a fruit that becomes 5 or 6 different products, with almost nothing left over at the end. The tomato processing industry solved its waste problem the way most of these stories actually resolve, by finding value already hiding inside a pile everyone had written off, rather than inventing something from nothing. 4 different, unglamorous uses turned up inside the exact same slimy mixture that processors had been trucking to landfills for a century. A pigment, an oil, a biopolymer, and a feed ingredient, each one waiting for someone to ask the right question. The tomato itself never changed. It has been growing the same waxy, waterproof skin, the same antioxidant-rich flesh, and the same oil-bearing seeds for as long as people have been cultivating it. What changed was the assumption sitting underneath more than a century of ketchup factories. The assumption that only the juice was worth keeping, and everything left in the strainer was garbage by definition. Once that assumption broke, in Israel in 1995 and in Spain decades later, the rest was just chemistry catching up to an opportunity that had been sitting in plain sight the entire time. If you want more stories like this one, where an entire industry's biggest headache turns out to be its next big product, subscribe to the channel so you don't miss what happens when the next unlikely waste stream gets the same second look.